this event and enlighten us with this important topic of engineering electromagnetics. I understand that electromagnetics or engineering electromagnetics is the base for any RF and microwave engineer. If you run away from this, you are not going to succeed. And our academic colleagues, they have been trying to innovate various methods to keep this subject, a little bit dry subject, attractive. And today's event is also one effort in that direction. So I'm sure that today's event will motivate more students to like this subject and not run away from that. With this, I wish all the best to the student one chapter of MTT Vardhaman Engineering College, and we look forward to this talk. Over to you,
Thank you, Thank you, Sandeep sir. Now I request Lakshmi Narayana sir, former chair of MTT chapter Hyderabad section, to talk few words.
Shravan, I think sir is facing some problem in joining. So let's continue.
Okay, ma'am. Now I'll request Suleksha ma'am to introduce our speaker.
Yes, I'm very much grateful to introduce our today's speaker, who is Professor Dr. Levent Sevgi. He is a fellow of IEEE. He received his Bachelor of Engineering and Masters of Engineering and PhD degrees in Electronics Engineering from Istanbul Technical University, ITU, in 1982, 1984, and 1990, respectively. In 1987, while working on his PhD, he was awarded a fellowship that allowed him to work with Professor L.B. Felsen at the Weber Research Institute or New York Polytechnic University, York, for 2 years. His work at the Polytechnic concerned the propagation phenomena in non-homogeneous open and closed waveguides. He was with Istanbul Technical University from 1991 to 98 and TÜBİTAK MRC Information Technologies Research Institute from 99 to 2000, Weber Research Institute, New York Polytechnic University from 88 to 90, Scientific Research Group of Raytheon Systems Canada, 1998 to 99, and Center for Defense Studies, ITUV SAM, from 93 to 98 and 2000 to 2002, and with the University of Massachusetts Lowell, USA, as a full-time faculty from 2012 to 2013, with the Douglas University from 2001 to 2014, with Istanbul Okan University from 2014 to 2021. So he has been an IEEE APS Distinguished Lecturer for the term 2020 to 22. He served one term in the IEEE APS AdCom from 2013 to 15 and one term as a member of IEEE APS Field Award Committee from 2018 to 2019. He has been the writer, editor of the Testing Ourselves column in the IEEE AP magazine from February 2007 onwards. And also a member of IEEE APS Education Committee since 2006. He has also served in several editorial boards of other prestigious journals or magazines, such as IEEE AP Magazine since 2007, Wiley's International Journal of RF MICAE from 2002 to 2018, and the IEEE Access from 2017 to 19 and 20 to 22. He is the founding chair of EMC Turkey International Conferences, and he has also been involved with complex electromagnetic problems and complex communication and radar systems for nearly 3 decades. His research study has focused on propagation in complex environments, electromagnetic scattering and diffraction, RCS prediction and reduction, EMC or EMI modeling, simulation, tests and measurements, multi-sensor integrated wide area surveillance systems, surface waves, HF radars, analytical and numerical methods in electromagnetics, FTTD, TLM, FEM, SSPE, and MOM techniques and their applications, and also bioelectromagnetics. He is also interested in novel approaches in engineering education, teaching electromagnetics via virtual tools. He also teaches popular science lectures such as Science, Technology, and Society. He has given dozens of seminars, invited keynote talks, organized, presented several tutorials, training sessions, and short-term courses from half a day to 3 days in universities, institutes all over the world. He has published more than a dozen special issues sections in many journals as a guest editor and also as a co-guest editor. Uh, he has published many book chapters in English and Turkish, over 180 journal and magazine papers, tutorials, and attended nearly 100 international conferences or symposiums. His 3 books, Complex Electromagnetic Problems and Numerical Simulation Approaches, Electromagnetic Modeling and Simulation, and Radio Wave Propagation and Parabolic Equation Modeling, were published by IEEE Press, Wiley in 2003, 2014, and 2017, respectively. His 4th and 5th books, A Practical Guide to EMC Engineering, which is published in September 2017, and Diffraction Modeling and Simulation with MATLAB, which was published in February 2021. These were published by Arctech House. And he also have given keynote talks in various conferences. There is a huge list of conferences, I can say. And his H-index is 35 with a record of more than 4,100 citations by Google Scholar. So with this brief introduction about the speaker, I would like Professor Lakshminarayan sir has able to join. Sir, can you speak a few words?
Thank you, Dr. Sulakshana. It's a great privilege for me to say a few words. I'm sorry I was facing this network problem on behalf of IEEE Hyderabad section and on behalf of IEEE MTT APEMC Society's Giant Chapter, and also on behalf of Vardhaman IEEE MTT Student Branch Chapter. We welcome Dr. Professor Levent Sevgi, fellow IEEE and IEEE APS and distinguished lecturer. It is a very exciting talk. Without losing much time, this is the first time I am listening to the title Engineering Electromagnetics to Electromagnetics Engineering and Teaching training for the next generations. Yes, I think it is a very useful talk to all of us. I think let us take it forward. We will thank Professor Levent for sparing his time. Let us listen to him. Thank you very much, Professor. Let's go ahead. Thank you.
Thank you, sir. Thank you very much, sir. Sir, Professor, please take over the session.
Okay, can we start now?
Yeah,
hello?
Please proceed, sir. Please proceed.
Okay.
Yes, sir.
So can you see the slides and the volume is okay?
Yes, yes, sir.
Okay. So thank you for the invitation and for your kind words. It's a pleasure to me to be with you, with young colleagues in Hyderabad section. So let's start the keynote distinguished lecture. As you said, the title is From Engineering Electromagnetics to Electromagnetics Engineering. When I was a student 40 years ago, it used to be Engineering Electromagnetics, but today we have to call it Electromagnetics Engineering. We will see why. I spent 40 years in electromagnetics, as you said, Sulakshana, in your introduction. These are the institutes and the periods I spent. My first university is Istanbul Technical University, and the last one is Okan University. It is also in Istanbul. I did my PhD in New York. I spent some time with Raytheon, Canada. I was the chair of National Research Institute, and also I spent 2 years with UMass Lowell in Massachusetts, United States. So I was lucky because I have spent years with famous electromagnetics professors. This is my Ercan Topuz from Istanbul Technical University, my first PhD advisor. And Leopold Felsen is a giant, late professor Leopold Felsen is a giant in electromagnetics. I did my PhD studies under his guidance. Another famous professor is the founder of UTD and PTD, Professor Ufimtsev, a Russian-American professor. And also Raj Mitra is another colleague, which I have collaborated for a long time. These are the titles of my distinguished lectures. The first one is this one, From Engineering Electromagnetics. I have also 4 others, Guided Wave Theory, Electromagnetic Diffraction Modeling and Simulation, From Design to Market Electromagnetic Compatibility Engineering, Wave propagation, and also antennas, arrays, and antenna calibration. And as you said in your introduction, these are the books I have published in IEEE Press, John Wiley, and Artec House. So these are the titles and abstracts of my other talks: Guided Wave Theory, Electromagnetic Wave Propagation, Diffraction Modeling and Simulation, EMC Engineering, and Antennas and Arrays. So I hope I will be given one of or a few of those other titles in the future in person, maybe in Hyderabad or in other places in India. Actually, the title is not new. We published a special issue back in 2006 with the same title. So we have been discussing this issue for the last 15 years or so. And here are a few of recent talks from India, Iran, Poland, France, Egypt, to all other countries and regions. Now, the next month, I'm hoping to go to United States and Canada for a series of distinguished talks, starting from October 15 to November 15, which will be in person. The first one will be with UMass Lowell about antennas, arrays, and calibration. Second one will be in Polytechnique Montreal in Canada, the same title, and also diffraction modeling. The other one with University of Toronto, diffraction modeling and simulation. MIT will be my next stop in November 9. And then Syracuse University, November 11. Also nearby another the same day, another topic, diffraction modeling and simulation. And the others, which are not sure yet, will be NJIT in New Jersey and Wentworth in Boston, and maybe Fairleigh Dickinson University in Boston also, in New Jersey also. So we are going to miss in-person seminars, webinars, because we don't want to have online seminars and conferences anymore. So here is the outline of today's talk. We are going to see a few slides about engineering, then about electromagnetic engineering, and we will discuss modeling and simulation approaches in electromagnetics, and we will see how we can calibrate, or we should calibrate, our softwares. And the last part belongs to teaching and training by using some of our electromagnetic virtual tools, which are simple packages. And the presentation will end with the conclusions and discussions. So let's start with engineering. Now, actually, we engineers solve problems. Life is problem solving, but it depends on the person and the discipline. So for a mathematician, showing the existence and uniqueness of the solution is the solution. But we are engineers, we deal with observable, which means computable or measurable solutions for real life problems under given conditions. So stability and accuracy of the solution is also critical, are also critical for us, for engineers. We engineers do not seek the best solution, neither the cheapest solution nor the fastest solution. Depending on the requirements, your budget, your time, the criticalness, we engineers have to seek the optimum solution. We are engineers, we deal with physics, real life, we use mathematics, conceptual life, and we speed up with computer. So real world, conceptual world, and synthetic world, there is an interrelation. Therefore, this necessitates an intelligent balance among mathematical background, engineering experience, and numerical simulation. So if you deal with engineering problems, you have to be very strong in terms of theory, practice, and computations. We speak with numbers, so a number can be given as a result of a measurement or a computation. Therefore, engineers, we need to well understand the definitions of accuracy, sensitivity, precision, and resolution. Very often, they are misused or confused. In addition, results are not meaningful without stating the error uncertainty limit with a given confidence boundaries. Actually, the real-life problems are not deterministic, are not stationary, are not linear, are not homogeneous. So we assume they are. So this brings error, uncertainty, and other problems. So we have to deal with them. For example, suppose you repeat a measurement n times and measure x. Then the mean average value x0 will be the addition of all the data and divided by the number of measurements. And the error, which is nothing but the standard deviation, will also be calculated by using this equation. So if you give a number, you have to try this with a given confidence limit. For example, 95% confidence limit, the measured or computed value is between x0 minus delta x and x0 plus delta x. So you have to state the uncertainty bound. Engineers never give a unique number as a result of a measurement or computation. Suppose you test a vehicle and measure the electric field in open field test site or anechoic chambers, as you see in some of these videos, in volts per meter. So here are some fundamental questions that every engineer should ask himself. Who will do the test and measurements? In which environments will the test and measurements be performed? What type of equipment will be used? Who will monitor and control these tests and measurements? Who will control and authorize everything, the process, the procedure? How will you be sure that everything is okay during these processes? How will you control systematic and random errors? How will you present the results, the reporting? So the keywords are authorization, accreditation, calibration, and certification. Remember, physics is a subset of mathematics, which is also a subset of the discrete world. So a mathematical solution may not be your physical solution, and a discrete solution may not be your mathematical solution. So it is your task, it is engineer's task to seek the physical solution in the discrete environment. For example, we know and use Fourier transforms since our undergraduate days. So this is the equation we use for Fourier transform. You give me a time signal from -infinity to infinity. I take its integral, which means I add up all the signals, and I can give you its frequency content in every frequency for every frequency resolution. So you have to observe the signal in the time for an infinite period. But what if you can observe only in a finite period, t, at some discrete time instance, delta t, like we do in our measurements or in our numerical computations? For example, the frequency content of a sine signal is f0, singleton signal. Mathematical Fourier transform gives signals at both plus and minus f0. So we have negative frequencies in mathematical world, but in real life we don't have negative frequencies. But if you take the discrete or fast Fourier transform, it gives you multiple harmonics, infinite number of harmonics of this signal. And in addition, if f0 beyond the maximum frequency, which is specified by the delta t sampling rate, it cannot be observed its actual frequency. Instead, it enters from the left because of the rotational symmetry and periodicity. So fast Fourier transform also gives signals at negative frequencies. So these are the DFT and FFT challenges: discretization, numerical integration, and finite time duration. So you have to pay attention to these two relations. The frequency resolution is equal to 1 over capital T, where T is the recording time. So the frequency resolution depends on your recording time. If capital T goes to infinity, then delta F is 0. And maximum frequency depends on the sampling rate, delta T. So in this slide, you will see how discrete and fast Fourier transform gives you ghost signals, non-realistic, non-physical signals. So suppose you have F1, F2, F3, and F4 as appeared at these frequencies. And suppose your delta T and capital T are chosen in a way that the gray area will give you minus Fmax and plus Fmax region. So under these conditions, only F1 will appear in its true frequency. The others, F2, F3, and F4, will appear as ghost signals. So you have to pay attention your discretization time and sampling rate. So if the signal record and sampling rate are not properly chosen, only one of 4 tones appears at its true frequency. So here you see a short video of 1D FDDT and non-resonant and resonating signals. This is the first resonance, and this is the second resonance. So resonating and non-resonating signals are totally different, which means resonances are critical in finite length in 1 dimension, in finite area in 2 dimension, and finite volume in 3-dimensional space. So you have to pay attention your resonances. This is a video you can find from the internet. It belongs to Tacoma Bridge, which was established in Seattle, Washington, USA in 1940, and it collapsed within 4 months. And engineers, only after this disaster, realized the criticalness of resonances in finite length, finite area, and finite volume structures. See how it collapsed. So resonances are critical, and unfortunate disasters teach us a lot. We also learn from our mistakes. So let's move to the second part, electromagnetic engineering. So the role of electromagnetic fields in our lives has been increasing. We have been surrounded by electromagnetic waves everywhere. Communication, remote sensing, integrated command control surveillance systems, intelligent transportation systems, medicine, environment, education, marketing, defense are only a few areas where electromagnetic fields have critical importance. Today we have systems with frequencies from DC, from 0 Hertz to terahertz, and with the sizes from nanometers to kilometers wide. Almost all of these systems are broadband and digital, so they have to operate close to each other, which means we have severe electromagnetic interference problems. So EMC engineering is also critical in today's engineering. Therefore, we have witnessed the transformation from engineering electromagnetics to electromagnetic engineering for the last few decades. So instead of calling microwave engineer, radar, EMC, antenna, propagation, VLSI, communication, biomedical engineering, we prefer to call them electromagnetic engineering. And these are a few sub-areas where electromagnetic engineering is critical. We have radio wave propagation problems, radar technology, microwave circuits, biomedical engineering, subsurface tomography, remote sensing, EMC, EMI, antenna design, signal processing and imaging, wireless communication, 4G, 5G, 6G, and we have new materials like metamaterials. So electromagnetics is critical in all today's technological problems. We are lucky because we have well-established theory, which is electromagnetic theory, stated with Maxwell's simple equations. On the left, you see Maxwell's equations in differential form, and on the right, you see them in integral form. Actually, differential means subtraction, integral means addition. So we should add only electric and magnetic fields or subtract them in the time and in the space. Maxwell equations establish the fundamentals of electromagnetic theory. Actually, in electrical engineering, we use both electromagnetic theory and circuit theory. Actually, circuit theory is a subset of electromagnetic theory, so there are no two different theories. Electromagnetic theory is the only theory in our field. New generations, young people may find these equations unattractive, but all we need is to subtract and add electric and magnetic fields in time and space, as I said before. So Maxwell's equations are general, are the solutions of every problem, but once you state your geometry, which means boundary conditions, Maxwell's equations plus boundary conditions will give you unique solutions for your problem. It may be an antenna problem, propagation problem, diffraction problem. We have analytical exact solutions, mostly in integral form or infinite series summation form. Unfortunately, we can find analytical exact solutions for only limited number of highly simplified, highly idealized problems. So for the last century, we have analytical approximate solutions, which we usually call them high-frequency asymptotics. And for the last several decades, we have powerful computers, so we have numerical solutions. Still, discretization, computation memory, and computation time are challenges in these solutions, in these methods. Theoretically, we can divide all electromagnetic problems into three: antenna and radiation problems, RCS, radar cross-section and scattering problems, and guided wave problems. And in all three, we use Maxwell's equations and boundary conditions, but we follow different paths for antennas, for scattering problems, and for guided wave propagation problems. So these are the discrete observables which we use during computation or during measurements. We have rays, either geometrical or physical optic rays. We have diffraction terms like GTD, geometrical theory of diffraction, UTD, uniform theory of diffraction, and physical theory of diffraction, PTD. We have modes for closed resonating structures. We have normal modes, adiabatic modes, and intrinsic modes. We can use beams, which means complex source point, pulse beams, and parabolic equation methods. Since they all have advantages and disadvantages with regions of validity, hybridization is critical. We can combine rays with modes with parabolic equation, or rays with parabolic equation. Lately, we can use time domain wave optics, especially for the numerical computations, such as wavefronts and potentials. So observable means computable or measurable. These are high frequency asymptotics, as I said before, GO, GTD, UTD, POPTD. The first three are ray-based models. The last three are induced current-based models. And these are some of the well-known numerical techniques: FTDT, transmission line matrix, TLM, method of moments, parabolic equation method, and finite element methods. The first two are in time domain. Method of moments, parabolic equation, and finite element are basically in the frequency domain. So when you face an electromagnetic engineering problem, you should consider the frequency range, the signal strength, time duration, discontinuities, which means impedance differences, and geometry boundary conditions. And among these, you have to take into account these relations: time frequency, where we use Fourier transform, frequency geometry, frequency impedance. So let's move on. The third part, electromagnetic modeling and simulation, which is critical for teaching and training young next generations. So we deal mostly with deterministic problems, and we search roots of nonlinear equations. We solve n by n systems of equations. We do integration, as in radiation integrals. We do differentiation, as in wave equations. And we need to do an interpolation and extrapolation, because we usually have finite data. So life is stochastic, so randomness, probabilistic, and statistics, error and uncertainty analysis, and the confidence levels or confidence percentages are critical. So there are different modeling and simulation approaches. We can use task trainer simulation. You have virtual reality simulation. You can have mankind-based simulations or live simulations, and physical-based simulations. Among these, the subject of this presentation is this one, physics-based simulation, and this is the definition. Physics-based simulation is nothing but computer simulations based on physical understanding and mathematical representation of a real-life problem, device, or system. So a model is a physical or mathematical abstraction of a real-world process, device, or concept. Simulation concerns with modeling of real-world problems. A simulator is a program or a series of programs. So why and when do we need simulation? Very often it is expensive and time-consuming to do tests with real systems. Sometimes it is dangerous to do tests with real systems. And sometimes it is impossible to do tests with real systems, because when the real system has not appeared yet, and in addition to them, we need to apply simulation if you want to play what-if type games, if you want to play the parameters and the geometries also. So that is the most powerful part of simulation. This is a generic picture of modeling and simulation, which we call electromagnetic package or electromagnetic virtual tool. So we have physical problem, real world problem. We apply a conceptual model, as in electromagnetics, we use Maxwell's equations, and then we write a computer program. So for the real world problem, there may be infinite number of conceptual models, but we choose the proper one. And for the chosen conceptual model, there can be infinite number of computer programs. We choose the right one. So very often we apply numerical analysis, and we need sometimes we need parameter optimization. And once these are ready, we can add computer visualization capabilities. We can design graphical user interfaces to make it better for the user. So in electromagnetics, we start with Maxwell's equations, we discretize and get the electromagnetic virtual tool. And the core behind every virtual tool may be in closed form, as in the left side, or open form, as in the right side. So closed form means you have matrix systems and unknowns with n equations. Open form, iterative representations. So closed form, you don't need to worry about stability, but huge matrices are required. Construction and computation may be a problem. Method of moments, for example, is an example for closed form virtual tool. In open form, small sizes and easy to construct, such as FDDT, finite difference time domain method, but the stability is conditional, so you have to pay attention to the stability conditions. So you have software and you need to calibrate your software. Let's see a few words about how you do the calibration. So when you build a model, you introduce assumptions, you neglect several effects, you do approximations and do simplifications. And in addition to all these, if you want to use a computer, you do discretization. So the first four belongs to analog world, the last one belongs to synthetic world. So it is a disaster to study in the synthetic environment. So you have to be very careful. So you need to apply validation, verification, and calibration. Validation asks the question whether the right model is built or not. On the other hand, verification asks the question whether the chosen model is built right. Calibration is nothing but testing the results or comparing the results with the reference. But what is the reference? Very often, in most of the cases, we don't have reference. So analytical exact solutions may be used as reference because we can get the accurate numerical data from analytical exact solutions. For example, flat Earth and two-ray model, which is very simple in terms of propagation modeling, that is used to calibrate open field test sites. For the antenna engineers, half wavelength dipole or horn antennas are used in antenna calibration. So analytical exact solutions are very valuable for us. Unfortunately, we don't have them very often. This shows interrelations in modeling and simulation with validation, verification, and calibration. We have real-world problem. We choose one conceptual model, and we do conceptual validity through physics-based analytical modeling. Once we choose the mathematical model or a conceptual model, we write our computer code. We need to apply code verification through computer programming. At the end, computer gives you a number, so you need to apply operational validity through numerical and physical experimentation. So we have two types of models, analytical and numerical. In analytical model, in the discrete environment, in the synthetic environment, you introduce your geometry with the analytical model, solve it, and then write your computer code and get the user data and get the result. So for the analytical model-based approach, actually you solve your problem, computer only gives you a result. On the other hand, for the numerical model-based approach, you do the discretization directly with the Maxwell's equations, get your numerical model, and then anybody who wants to use this model applies his geometry or circuit, then write computer code and obtain numerical results. Here you discretize the problem, computer solves it for you. Actually, you make the computer solves it for you. Let me show you a few examples. For example, this is analytical model-based approach. We have introduced antenna array package in the IEEE Antennas and Propagation magazine 15 years ago, maybe. And you can locate a number of radiators and see how radiation characteristics change. For example, on the left, you see the linear, on the right, circular arrays. And you can change the number of elements and get the frequency and get the results. This is an analytical model-based approach because there is only one equation behind this tool. It is this equation. So you write all contributing sources or antenna array elements with this equation and get the results. The rest is designing a graphical user interface and some fancy plotting and video capturing. So this is an analytical model-based approach. Another example for analytical model-based approach is to find ray paths through homogeneous atmosphere, which are emanating from a transmit antenna on the left and a receive antenna at point A. So you have direct rays, ray 1, you have red one, reflected wave number 2, and tip diffracted or edge diffracted rays number 3. So you write each individual contributing rays, add them up and get the field at the receive antenna. So you solve your problem. This is also an analytical solution. So if you move the receive antenna to point B, you have only diffracted rays and secondary reflections. So this is an analytical model-based approach. You have to find the contribution of each existing rays there. But this one is a numerical model-based approach, example 3, because you apply ray shooting. You shoot the rays from the transmit antenna. You divide the layers into small parts like N1, N2, N3 with the refractive index, and then you apply this Snell's law, and then see whether this shooted ray approaches receive antenna or not. And this is a ray shooting algorithm, which is pure numerical model. So geometric optic ray summation is an analytical based model. You calculate the contributions of each eigenrays, but geometric optic ray shooting is a numerical based model. You discretize the medium and shoot the ray. Ray paths are plotted by the program automatically. For example, this is an example for ray shooting. On the left, you see three-section, linear refractivity profile, n versus height. And for this refractivity profile in homogeneous atmosphere, you observe how rays are bent from the source. So this is a ray shooting virtual tool. For another linear refractivity profile, you observe how rays are travel through this inhomogeneous medium. Ather example for numerical based approach is the parabolic equation model. For example, you have two-dimensional Helmholtz wave equation, z is height and x is range, but you do approximation and get this equation. which is called parabolic form. And this one is two-way, this one is one-way model. So what you need to do is to apply FFT, Fourier-based parabolic equation. On the left, you have a vertical antenna pattern, and then step by step, you move it towards the right using this equation. So give me your vertical initial field profile, and I apply Fourier transform, a complex multiplication, inverse Fourier transform, and I get the field delta x away, next step. So then I move this as the next initial field profile and repeat the same, and I trace all the ranges with this simple equation as you see here. So one-way parabolic equation model. So you have source here, you have ground here, and the propagation from left to right is video recorded here. So you can tilt the beam and see how tilted beam reflects from the bottom, from the ground. You can change the refractivity and see how rays are bent through inhomogeneous atmosphere over in terrain profile. You can also apply parabolic equation on the other way, backwards, and get two-way parabolic equation model. You see here, we have infinite reflection wall here. So if you repeat the video, the waves are propagated and then reflected wave. So they interfere and they form maximum and minimum. Another example, you have infinite termination here and also knife edge type objects here. So you have propagating and reflected waves, but in between here, you have multiple back and forth reflections. So you can take into account all kind of physical activities there from source to receiver in your propagation problems. You can also use time domain Maxwell's equation as in this virtual tool. You can plot terrain profiles and then send the line source and observe how electromagnetic waves in the time domain. The previous ones were in the frequency domain, but this one is in the time domain. You see, in the time domain, you can change the colors and the students can play with each of them. So how do we test our pure numerical models? We need analytical reference model, a linearly decreasing refractivity profile with the 2D wave equation, which is the Airy equation, gives us analytical exact solutions in terms of Airy functions. So we can use this scenario for calibrating our reference solutions. So these are the Airy functions. For the negative x values, we have standing waves like sine waves, but for the positive x's, Airy function gives you exponentially decay functions, evanescent waves. And here we call turning points. So you use them as the modes of your problem, and then you add them according to your source distribution and get the results like this one and this one. So mode summation is nothing but Fourier series representation of any given source function. So if you add more and more modes, the source and its Fourier transform matches very well. This is another video showing analytical and numerical solutions, how they agree and how they propagate through the surface duct problem. So visualization is critical. Now, although this is a reference solution, packed flat Earth with linearly decreasing atmosphere is a reference solution, its numerical computation may be a challenge, especially if you vertically tilted the excitation. So here, tilt angle on the left, 0, 2, 4, 6, 8, and 10, and the number of required modes for each case are also shown on the right. So if you don't tilt the angle, then only less than 20 modes may be enough to represent your source. but for 10 degrees tilt angle, either downwards or upwards, you may need up to 8,000 area functions to represent your source. So maybe a critical numerical computation of an exact reference solution may be a challenge. You have to be careful. So once you have your codes, then you can compare. On the top, you see analytical solutions for two types of vertical antennas. One is up tilted, the other one is down tilted, and the bottom is perfect electrical ground. And you see how they agree. Analytical and numerical solutions agree. So these are vertical comparisons between analytical solutions, parabolic equation, and also we add finite element. You see almost perfect agreement are obtained if you pay attention to the discretization requirements. You can also test against knife edge problems. So you have a knife edge problem here. The observation may be here, A, or B here, C here, D here. So for this source and receiver locations, you need 4 different rays. The direct ray, if happens, the tip refracted, ground reflected on both sides. So if you add them, you get the 4-ray models. So here, the 4-ray, the analytical model at the bottom and parabolic equation pure numerical bottom model on the top. You see how they agree. Other examples. So this is the book about parabolic equation modeling, which we published in 2017. It contains all these propagation models and virtual tools. So the last part, teaching training with electromagnetic virtual tools. Now, why we have been developing and sharing these kinds of virtual tools? As I said in the beginning, my first university is Istanbul Technical University. That is the oldest university in Turkey and within top 3 among engineering universities. Almost 2.5 million high school graduates enter a general nationwide university exam, as in your case in India, and you need to be among the top 0.01% within top the first 1,000 or 2,000 students in order to join this university. But my last university, Istanbul Okan University, is a 20-year-old foundation university, not within top 100 among 207 universities in Turkey. You can join Okan University if you are within top 400,000. So the first one is has very high level students, but the second one well below average level students. So the question, how can you teach electromagnetics in these two different universities? You have brilliant students in the first one, but well below average students in the second one. So you need to teach electromagnetics to these different level students. So that's why we use electromagnetic virtual tools. So here you see some commercial packages. There are dozens of them, but the core computing methods are either FDDT, TLM, finite element, method of moments, parabolic equation, or high frequency asymptotics among all these commercial softwares. So you do hybridization in these softwares. So in order to use them intelligently, first you should use very basic and very simple virtual tools like ours. So that's why we have developed and introduced multi-purpose electromagnetic virtual tools that can be used in most of these classical lectures. We have always looked for something which would be useful, give physical insight, and effective so that young electromagnetic students and researchers can use them intelligently. Note that these virtual tools should be very simple to use. The user should be able to change parameters. Some parameters should be fixed so that the user, the beginners, will not get lost. It should be open to non-physical results to some extent so that the user may comment on them. These are the philosophies behind our virtual tools. And this is the generic front panel. Usually we have geometry parameters here. Then you choose boundary conditions, you define your source, and then you run or plot the simulations. We have two-dimensional graphics, or we have time domain simulations. So this is a generic front panel of our virtual tools. These are some of the virtual tools that we have developed and shared for the last 20 years about propagation, antenna, guided wave theory, both undergraduate level and graduate level tools. We have diffraction theory tools. So let me show you a few from them. This is an RCS radar cross-section prediction. So this is a three-dimensional method of moment and FDDT package. All you need is to introduce 3DS graphics files of real object, maybe aircraft, it may be ground vehicle. So the program automatically generates the discrete FDDT mode on the C part, and in D you see the method of moment discrete model of this DC-10 airplane. So then you send electromagnetic pulse in the time and observe and record transient effects, scattering effects. This is within a few nanoseconds, and then you apply Fourier transform and get the results. Here, another example, F-16 aircraft, single aircraft at the bottom. On the left, you have two F-16 aircrafts. So you run FDDT, then record time domain transients, then you run FFT and get the frequency domain object and plot RCS versus angle, as in these examples, for examples. So once you have a calibrated virtual tool, you can play what-if time games. For example, what if I fly two F-16, one on top of the other or side by side, and here the RCS characteristics versus frequency. The red one belongs to one F-16, the dashed blue one belongs to two F-16, and this is the radar signal. So you see how they differ for one and two aircrafts. Then you can get diffraction theory, scattering, diffraction, and then obtain different plane waves. For example, total fields. This is a perfectly electrical strip in 2 dimensions. If you subtract the incident wave, you get the scattered fields. On the left, you have total fields. On the right, you have scattered fields. So you have shadow regions, reflections, interference. You change the angle of illumination and get different videos. So these are very useful to show students how electromagnetic waves scatter, reflect, diffract, or refract. This is another tool about diffraction problems. You see, this is a wedge problem. You send waves for different types of boundary conditions, and you see how reflected and diffracted pulses occur around the wedge, and then you can plot total fields, and then you can see the total fields on the left and only diffracted fields on the right, obtained with different analytical and numerical models for other wedges and for other angle of illuminations, incident waves. And we collect all these in our recent book published this year. So now the conclusions. So wave-oriented electromagnetic engineering is an effective way of identifying both technical and educational challenges in a rapidly changing, internet-driven, globalized world. Computer capabilities has revolutionized the analysis of complex systems. Therefore, modeling and simulation and validation, verification, and calibration are crucial. Engineers need to well understand physics behind mathematics before using simulations and compare numerical results, experimentation. keep in mind the assumptions and their validity ranges. You may look at the object sometimes as a whole, but also you need to pay attention to every detail in terms of different electromagnetic phenomena. And multiphysics has become essential to establish interdisciplinary collaborations. Although new approaches such as virtual reality or artificial intelligence are very attractive, hands-on training is a must in electromagnetic engineering education. So basic lectures such as measurement techniques should be renewed accordingly. Teaching training via our electromagnetic virtual tools is highly effective. Students first play with these tools, visualize electromagnetic wave object interaction, reproduce the results of the given scenarios, and then create their own scenarios. They then start electromagnetic theory and play with Maxwell's equations. So this establishes understanding physics, mathematics relations. Students who are further interested in electromagnetics in their research, you can get the supplied source codes and modify them and develop better ones. So today's engineering students are very lucky because there are excellent commercial packages and measurement devices. But also today engineering students are very unlucky because of these excellent commercial packages and measurement devices. So this is the motto I used in my first book, Let's Do It. And this is the second book motto, Yes You Can. And this is the IEEE motto, tell me, I'll forget, show me, I'll remember, involve me, I'll understand. So this is the end of my presentation. Thank you.
Now I request our panelists. I'm getting the sound, sorry. Yes, sir.
Excellent lecture. Covered entire electromagnetics, right from basics to advanced ones, scattering, numerical, analytical techniques, and how to make the students understand. Very great.
Thank you.
But some of these things, whether are they available commercially, some tools, I don't know, because I never tried for these things. I think Sulakshana should try to get some of these virtual tools which are already available instead of trying to develop them.
Yeah. Now, you can download them from our personal web pages. Also, you can send us emails because we can then send you the latest versions of those virtual tools.
Sulakshana, may I request you to get these things?
Yes, sir. Yes. I was thinking the same. We can use those, graphs and videos to show our students so that they can understand very much. I'll write a mail to you, sir. Please, if possible, please share those with us.
Sure.
Because I do give a lecture, but I'm not a regular lecturing, but I do give some motivational lectures. We need to do that to make the students more, to involve them in the area of electromagnetics and microwave engineering. Right, that's what a lot of mails were getting exchanged today. Also, I saw from Yogesh Verma, Sandeep, and PVD Somsekhar Rao. Well, I was just observing, and I think it is the right time we had this lecture from Professor Levent Sevgi. So it's very useful. Thank you, sir.
Thank you.
So, thank you very much, Professor Sevgi. You have really taken us through, those so-called tedious equations, as the students call them, and how to make them interesting by adding the visualization capability to those equations, because then you really start understanding why those equations are important, and start enjoying them. And it's very kind of you that you agree to share what you have done over the past 20 years to the academic community. I'm sure they will leverage this generous offer and build upon that. One question I had, whether I see that most of your codes are developed on MATLAB, which is again a paid tool. Whether people can use open source tools like Scilab or something similar to run these codes.
We share our virtual tools both in C++ and MATLAB, but the ones in MATLAB are very easy to start and to handle and to modify. So if students want to take the M files of the virtual tool and develop or translate it to any others like Python or some other new languages, they can do that. But for today, MATLAB is the simplest platform for the undergraduate students.
Yeah, thank you. Thank you so much.
Yes, sir. Hello.
Hello.
Am I audible?
Yes,
I can see your hair, but not your face.
Okay. Yeah. I'm from Ethiopia.
Yeah.
Yeah, it is an interesting topic that you raise, sir.
Thank you.
I take one course in electromagnetism.
Which part of Egypt are you from?
Sorry.
Where are you from?
Ethiopia.
Ethiopia, I said, yes.
Okay. Yeah.
So I'm graduated in electrical and computer engineering, specializing in industrial controlling. So especially this electromagnetism, it is very interesting thing while I'm studying. Even if it is both in calculation, also physics part, also maths is there. So as a chance, I haven't get it in practically, but you raise so many topics. Even I'm looking for further study also. Those who raise you compare it, especially modeling and the simulation part, yes. Also, I am using, while I'm doing project, I'm using especially in for simulation part in big microcontroller, yes, the software that is. Also,
do you have a question for me?
Yeah. So can we get the especially the PPT?
What is PPT?
Yeah, the slide that you are.
The copy of your presentation.
Presentation material. Presentation slides.
Okay. It's a huge file, so it's not easy to send it to you, but a PDF copy. I can prepare a PDF copy and send you. Or Lakshana, maybe she records. She has already recorded this session. You can watch the video.
Okay. For
just
further,
send me an email. I can send you PDF file. Okay.
Okay. It is possible if you share your email also. It's possible. Where I am sending.
Okay, I will share his email ID. You can put a request to him.
What I suggest is like Dr. Sulakshana can collect this PDF copy of the material, and then it can be circulated to all those who are interested.
Yeah,
that would make it simpler.
Thank you, sir.
You're welcome.
Sir, good evening, sir.
Hello.
Sir, good evening, sir. Myself, Palguna. So I have this doubt. I mean, like, after seeing a model, how to know that whether it is an analytical model or mathematical model? How to distinguish?
Excuse me, I don't understand the question.
After seeing a model, how to know that whether it is a mathematical model or numerical model? How to know that, distinguish?
You should check the documents. If it's a commercial software, it has documents. It tells you what kind of methods, analytical or numerical or in hybrid form. If it's a paper, then you read the paper and get the information from there.
Okay, so document is necessary for knowing whether it is that one. Okay.
No. If you have a problem and if you want to use a commercial package and or if you want to develop your own code, your own program, if you are able to find analytical solution for your problem, it is best to write a program based on analytical model and then do numerical computations. But unfortunately, real life problems, they don't have analytical exact or even analytical asymptotic solutions. That's why we refer to numerical solutions. For example, this antenna system on a microstrip layer, you can find analytical solution. So numerical simulation is the only way.
Yeah, we have to put the equation and do that.
Yeah.
Yes, sir.
Yeah.
And also, I would like to get that softwares to teach also, sir. Selection madam, can you forward me that mail? I can send that and.
Yes. Yes. Sir.
Thank you. Thank you.
Yeah. My email address is ls, the first letter of my name, L, and the first letter of my last name, S, Levent Sevgi, ls at leventsevgi.net. You can easily do Google search and find all my email addresses.
Okay, sir. Thank you.
If you do Google search with Levent Sevgi electromagnetics, then you'll find all of them.
I'm putting your Gmail ID in the chat box, sir.
Yeah. Thank you. Thank you, Sulaksana.
Yeah, good evening, sir.
Good evening.
Yeah, sir, we have seen a number of commercial tools based on FEM, based on FEM, based on FDDT, based on MOM. But I don't know the reason why the simulation tools which are based on FEM is popular. Why not the other models like FDDT is as good as MOM?
I don't say that. FEM is not popular. All of them are popular depending on the groups, societies, electromagnetic problems. So for me, for example, method of moments, it's there for nearly 80 years, nearly a century. Method of moments is the first numerical method. It went back to 50s. Okay. And FDDT, finite difference time domain, is again for me is the best one to visualize electromagnetic waves directly in the time domain. So nobody can say that this method is much better than the others or much famous than the others. It depends on the problem and the groups.
Okay, yep. Thank you. Okay, sir, thank you.
So I believe that's all.
I think, Dr. Sachin, we can go over the next part.
Yes, sir. Yogeshwar sir, he is there in the meeting. You'd like to?
No.
Does he like?
Is he there? Is he there? I am not able to find his name.
He was there.
Yogesh?
I saw him, sir.
Yogesh? Yeah, Yogesh Verma is there. Yogesh.
Yeah, good evening.
Good evening.
Yes, sir.
Good evening.
Good evening, sir.
Good evening, Professor Sevgi.
Good evening.
Yeah, wonderful talk. After a long time on electromagnetics, we were looking for this talk for a long time.
Thank you very much.
And thank you for being part of this activity.
Maybe next time I'll visit you in person.
Yeah, that is what we would be looking for.
We look forward to that, sir.
I was in Hyderabad in, I think, December 2018.
Yeah.
True. So we are just waiting for the travel restrictions to get eased out, and then on the first opportunity, we are going to invite you.
It will be, in fact,
maybe next year.
Our pleasure to have you in person here.
Thank you very much. Maybe next year.
Yeah.
We can have some workshop type of thing, not just one lecture.
Yeah. Okay. So I believe this is the end of this session. Sulakshana.
Yes, sir. I request our volunteers to propose vote of thanks.
Am I audible, ma'am?
Yes, you are.
Thank you, Professor Levent, sir, for taking your time and spending with us. Ma'am, can you please share the memento?
Yes. Wait for a moment. I see Jabbar sir is present in the meeting. Sir, Jabbar sir, you are welcome, sir. He was just there. I just saw our branch counselor Jabbar sir has already joined. So only 1 minute.
Arif was also there. I saw Arif also. Arif Sohel also. I saw him. His name Arif Sohel.
Yes, sir. He was there. I think now I don't find him, but maybe like in the first part he was there.
Yeah.
Only 1 minute, sir. Hello, sir.
Jabbar.
Shravan, please go ahead.
Ma'am, can you please share the memento?
Yes. I also request all the participants to please fill the feedback form. I am sharing that in the chat box.
And Dr. Sulakshana, you can also share the link for the quiz that you proposed, right?
Yes, sir.
You don't miss out on that.
Yes.
So we have prepared a small quiz consisting of about 10 questions. Very basic questions. I'm sure students will find it very interesting. Those may be new for the professionals, but for students it will be able to attempt that.
Sorry, where is the link?
It will be shared.
Sir, I will share in a moment, sir. Let me share this memento, then I will share.
Thank you, Professor Levent, sir, for taking your time and spending with us. As being an undergraduate student, your talk helped me very much, and I guess it's same with other students as well. I thank you on behalf of Vardhaman Student Chapter, MTT Student Chapter, and IEEE MTT Joint Chapter Hyderabad section. Thank you, sir, very much.
Thank you.
I request Sandeep, sir, to say a few words.
I think we have already been talking, so we probably would not like to hold Professor Levent Sevgi for too long now. He might have other engagements, but it's been a pleasure to hear you, sir. And as all my seniors expressed, that we look forward to host you in person whenever it becomes possible on the first note. So and we will be looking forward. We have a very deep desire to make this field more interesting for the students, so that they take RF and microengineering, because everyone, you must, I mean, I think all of us agree that everybody is running towards software and coding. We want to turn things around, and with the applications of RF and microwave growing, with 5G, 6G, Internet of Things, Internet of everything, IOE, Internet of Everything. I'm sure we need good EM engineers who understand the subject in depth, and we need such lectures more and more in future to attract young engineers.
Yeah.
So thank you very much for taking your time.
Thank you.
We look forward to hearing you again.
Okay, stay safe and see you next time.
Thank you.
Bye bye.
Thank you, sir.
Bye.
Thank you, sir. Thank you so much.
Thank you.
Bye bye.
Sir, 1 second, sir. Can we have a picture, please?
Take.
Yes, sir. One picture with you. Yes, sir. It has been taken.
Okay.
Thank you for joining us.
Okay. Thank you, everyone.
Thank you.
Thank you, sir.
Now I'll post the quiz, sir, to all the participants. Thank you.
I will not be joining the quiz. Let it be given to the others. Okay.
It's not meant for you, sir.
Right. Thank you.
Thank you, sir.
Okay,
all the best.
Thank you. Thank you.
Bye bye.
Bye, sir.
Yeah. Where is the link?
I'm sharing it now. I will send the link to your email IDs also.
Okay, yeah, that is possible. What
Yes,
about the material?
The material also will be shared.
Okay, see you.
Yes.
Okay, goodbye. So shall we leave?
Yes, you can leave. You can get the link in the chat box as well as in the email.
I will wait.
Yeah. Yes. The form is posted in the chat box now. You can access it.
Yes, not come. Hello.
We are ending the session now. Thank you.